The invited speaker and the chair of this session is Dr. K. Sriram. I request Dr. Sriram to please come on the dais.
Yeah,
Oh, right, sorry. Now I request Professor Najmul Hassan to present a token of gratitude to Dr. Sriram.
just a word before Sriram starts. The success of a person, there are two sets of people who really feel happy if you succeed. One are the parents, and the second set are the teachers. If your students do well, then we genuinely feel happy and proud. And Sriram is one of our students which has made us really proud. He's doing extremely well in research. He's a good academician and he's far to go. So very happy to have had him as a student sometime.
Before I ask Dr. Sriram to deliver his lecture, I'd like to take this opportunity to introduce our distinguished speaker. Dr. Sriram is a well-known figure in the field of astronomy and is currently working as assistant professor in Department of Astronomy, Osmania University. He specializes in the study of X-ray timing, spectral properties of black hole sources, neutron star source, white dwarf source, and supermassive black holes. Dr. Sriram has obtained his PhD from Department of Astronomy from Osmania University and postdoc from Korea Astronomy and Space Science Institute, Korea. With over a decade of research experience, he has published 62 papers in reputed scientific journals and has made a significant contribution to our understanding of the universe. In addition to his impressive research portfolio, Dr. Sriram is deeply committed to mentoring the next generation of scientists. He is currently supervising 8 PhD students. Dr. Sriram's expertise has been recognized by the prestigious organizations worldwide. He is a member of Astronomical Society of India and South Korean Astronomical Society. Moreover, Dr. Sriram has earned several fellowships, including the Korean Young Scientist Fellowship. He's a visiting fellow at TIFR Mumbai and an associate at IUCAA Pune. He has successfully completed 2 projects funded by DST and UGC respectively. Currently, he is handling 2 projects related to studies of neutron star X-ray sources funded by ISRO and studies of third bodies in binary systems funded by DST SERB. Please join me in welcoming Dr. Sriram.
Thank you, and foremost, I would like to thank my guru, Professor Hassan sir. I took the token of gratitude today. I am very happy for that. I would like to thank organizers, Dr. Rizwan and Dr. Priya Madam, Manu, that they have invited me to give a talk in my research field. So let us start the talk. Maybe most of you people are not from astronomy background, so I'll start from the scratch. Okay. So there will be a bit of basics and then I will show what kind of research me and my team is right now working on and what sort of facilities we are using, both Indian based space satellites as well as abroad. So let us move on. The talk, my talk title is basically X-ray view of black hole and neutron star binaries. So yeah. So basically, outline of my talk is I'll be talking about X-ray binaries, formation of accretion disk, which is extremely important in order to understand the X-ray binaries. Then I'll be talking about some spectral and timing features of black hole sources and neutron star sources, and how do we model the spectrum emitting from these sources. And I'll be talking about something a very unique features, timing features, which are known as periodic oscillations, which are very extremely important in order to know the nature of the source, whether it is a black hole or a neutron star. And then I'll talk about some of my research results. So X-ray binaries, broadly speaking, it is any single black hole you can't see because it will not emit anything. It has to be in a binary system. And in binary system, the compact object, the compact or the primary source could be a black hole or it could be a neutron star. And there are some classifications which I have written, Z sources, et al sources. So need not to bother about the nomenclature. Just try to understand the topics. Their X-ray luminosities are very high, 10 power 37 to 10 power 39 ergs per second. So if you see the X-ray luminosities of sun, which is of the order of 10 power 28. So these sources are 10 power 10 times brighter than our sun. So you have to understand these are primarily X-ray emitters, and in order to study these uh, X-ray emissions, we need space observatories because Earth atmosphere absorbs these X-rays. And right now we have number of confirmed sources, 60 to 100. I'm talking about in our galaxies. Uh, there may be a few detection in other galaxies also, but the number is very less. So there are candidates like 300 need to be confirmed. See, confirmed source means we know that it is black hole source. There are some methods by which you can know it, but there are some candidates. Candidates means we don't know entirely. We don't know whether it is a black hole or it could be a neutron. Now, this is the basic structure which we understood, like I can say that last 40 years, what we have dedicated in order to understand these objects. And this is the picture which we got that. So at the center, you have a black hole. So this is the accretion disk. Yeah, this is the accretion disk. At the center, you can have a neutron star or a black hole. This is a binary component, typically a solar type or some massive solar type star. And the matter is actually falling from this star to form a accretion disk. This is accretion disk. These two structures, elongated vertical structure, these are known as jets. So what we try to do is by studying these accretion disk and the jets, can we constrain the nature of the compact object? That means whether the central object is a black hole or is it a neutron star. So why we should study these X-ray binaries? They are extremely important, as I mentioned here. So it is the only prototype system in the universe to robust the nature of the compact object, because we can't have these objects in our labs. I mean, still the technology is not there to create these sources in our lab. So we have to rely on these astrophysical objects only. We don't know how the matter behaves in extreme gravitational fields, because we, as Professor Suresh was talking about, the gravity is basically space-time curvature. So we don't know how the matter behaves. So these are classical laboratories in order to understand the behavior of matter in the intentional gravitational fields. Most important being the jets. Most of these jets, they are seen in X-ray binaries, they are seen in young stellar objects, they are seen in, there is something called active galactic nuclei, which one of my students will talk about. So we don't know about the jet production mechanism. So again, these sources helps in understanding these objects, and there are few other things which I have written. So there are main point is how does these accretion disk form? So there are two theories for that. One is the stellar wind. So you have a massive star like 2030 solar mass, and we know that these stars actually have these strong stellar winds, and these wind particles are captured by this compact object and they form a accretion disk, and from these accretion disks we get X-ray emissions. Whereas there is another way which is known as Rose lobe overflow, in which the stellar wind is very, very less. It fills something called Loch lobe, and the matter will slowly transfer to the gravitational potential of this compact object, and they form accretion disk. Now this is the formation. I'll not spend much time. So matter pass through this something called Lagrangian point. You might be hearing about this Lagrangian point because of the Aditya launch. There was a lot of discussion in the media also. And as the matter pass through this Lagrangian point, it is that particle will capture by the compact object, could be a black hole or a neutron star, and it forms a continuous stream of rings, and eventually it will settle down, and that structure is known as accretion disk. And this is the basic some equation. So it is in the accretion disk, the half of the gravitational potential energy is liberated, whereas the remaining half is still stuck in the accretion disk. And as it encounters, as the matter encounters the surface, it hits the, if it hits the neutron star surface, you will see a lot of radiation coming out. And if it goes beyond the black hole event, the whole energy is lost. Okay, and these are the efficiencies. You can see that this is the efficiency for the white dwarf. It's 0.003, which is very, very less. And coming to the black holes, it is 0.006 to 0.42. 0.006 is for Schwarzschild black holes, and 0.42 is basically for Kerr black holes, which are basically spinning black holes. And this I would like to actually, Eddington luminosity is a very famous concept in astronomy, where any particle which is orbiting the star or a black hole, the radiation pressure because of the star or the black hole is balanced by something called gravitational pull. And if you put these equations, you will get there is something called luminosity, which is known as Eddington luminosity, and you can see it is only proportional to the, I mean, related to the mass of the central object, whereas the other terms are actually constant. So in a way, if you measure the X-ray luminosity, you can know the mass of the black hole. But this is an indirect method by which you can say what is the mass of the black hole. Yeah, this is the typical outburst, X-ray outburst. So this is one source, black hole source at 1743 minus 322, and suddenly the X-ray counts has increased. So don't think that these sources are always emitting X-rays. Sometimes, most of the time they do not, but sometimes they go for X-ray outburst, and the X-ray count suddenly increases, and we can see this is known as something called light curve, where the intensity is changing with respect to the time. And this is a diagram based on which we try to know the variation of the count rate of a particular source. In this case, it is a black hole. This is known as HID or CCD, which is hardness intensity diagram or color diagram. So during the outburst, at the onset of the outburst, the source is in this direction, and at the peak of the outburst, the source is here. And when the outburst is almost close to the low counts, again it goes back. So this cycle always continues. This is a spectrum of the accretion disk, which is very close to the black hole, and the X-ray luminosities are very, very high. So you can see here the spectrum goes from 1 keV to almost 10 power 4 keV. I don't know whether you have some idea, but 1 electron volt correspond to 11,000 Kelvin. So we are talking about 10 power 7 to 10 power 8 Kelvin. It's very hot, and that hotness is needed to emit the X-rays. Okay, so you can see there is a lot of variation in the spectrum. The spectrum is not constant. By studying the variation in the spectrum, we can know to some extent whether that source is a black hole or a neutron star. These are the intensity variations for neutron star systems, a special class which are known as Z sources. You can see that they are almost constant. Okay, you can see that there is no variation. But if you study the hardness intensity diagram or color diagram, you will see special tracks which are known as Z tracks. So by studying the spectrum and timing properties at each branches, for example, this is known as horizontal branch or normal branch. By studying the spectrum and timing properties here and here across this variation, you can tell how the accretion disk or how the matter behaves around these neutron stars. These are another class which are known as atoll sources. Again, you can see this variation is different than the previous variation. And let me tell you, both of them are basically a neutron star only. Okay, both are neutron stars, but you can see there is a huge variation. So something is happening with the X-ray variations. So these are the spectrums. So it's very different from the spectrum what you see in material science or some solid state physics. Uh, so these are the spectrum. Again, you see that neutron star spectrum are very weak. I mean, above 50 keV, not much counts are there. And it also varies. Okay, you can see especially above, this is 50. So above 50, the counts decreases. So we use different models in order to explain the spectrum, because by fitting these models, we can know basic properties like what is the disk radius at one particular X-ray luminosity, what is the Comptonization, how much Comptonized photons are coming to you. So you can see in the previous slides I shown you, for example, here the spectrum is very soft. You can see there is a peak. This peak is almost like a black body. It's not a black body, but you can approximate as a black body. And in some sources, you see that the peak goes at 100 keV. See, you can't have a black body at 100 keV. You should understand that. You can't have a black body temperature of 100 keV. You can't do that. Okay. So this, the reason for this peak is there is something called thermal Comptonization model. So basically, it's Compton effect, which we have studied in your graduation or post graduation, but it is inverse. In Compton effect, the photon loses the energy, whereas in inverse Compton effect, the photon gains the energy, and hence you will see this effect in the black hole source as well as in neutron star sources. So the idea is, I told you about the accretion disk. So each ring is emitting like a black body, and when you convolve it, you will see a spectrum like this. So the peak will not be a sharp peak, whereas it will be a broad peak. And the temperature of the disk varies as R power minus 3/4. This is a standard model. So hard X-ray component, which is like above 10 keV, which we are least known. I mean, we have a good physics about it, but exactly which process is going on, still don't know. There is a lot of research activity going in this direction. Okay, and there is a inner region of the accretion disk which we call corona. So this is not the corona which we are suffered. This is Comptonization region, and in order to explain the corona, we have a lot of models: thermal Comptonization, non-thermal Comptonization, or it could be a jet. So I just would like to skip the math part. So there are geometries, because these spectrums, what I shown you, in order to model this, you have various geometries. So these are the geometry we often use. So you have slab sandwich geometry. This is spherical disk geometry. This is patchy corona. So in order to explain different source spectrum, we sometimes we change the geometries in order to unfold the spectrums. We have to do that, especially when you are studying supermassive black hole accretion disk. We have to do that. So yeah, I just shown you. So this is, I don't know whether you can see this. This black spot is basically a black hole source with an accretion disk, and these blue dots are actually the jet component. So material is being ejected from the central region, and you have these jets. This is from one of the X-ray satellite, which is Chandra X-ray satellite. So I will read it. These are some timing scales which are very important, but I'll skip this. Yeah, the one of the most important tool what we use is in order to understand the timing behavior at high resolution is basically the power density spectrum. Most of the people are doing research; they know what is the power density spectrum. So basically, we can get the information based on the frequency domain. So that is the power density spectrum, and you can see this is this red light curve variation. This is the blue curve variation. You can see this is a low frequency periodic signal. This is the high frequency periodic signal, because this is the lower component of the periodic signal. Whereas you can see some fast fluctuations inherent to it, and this is the high frequency periodic signal. So same thing we try to apply in order to understand the timing behavior of this black hole or neutron star sources. So this is the power density spectra of neutron star source CoX1, which is one of the brightest low mass X-ray binary in our sky. And you can see these are the strong, they are not exactly periodic. So that's why these terms comes the quasi-periodic oscillations. And general theory of relativity predicts that by studying these quasi-periodic oscillations, you can know the mass of the neutron star. So in astronomy, let me tell you, if you know the mass of the some star, and if you know the distance of this star, there is a theorem which says that you can entirely tell the evolution of that particular source. And that's why any theory, if you give the mass or the distance, that is considered to be extremely good theory. Okay, and why we study these features? Because by studying these features, we can know the mass of that particular star. Okay, you can see these are low frequencies. These are like 10 hertz or 20 hertz frequencies. You can see there is something called high frequency component also, 1000 hertz. So try to imagine that the matter is orbiting at a rate of 1000 hertz nearby a neutron star. Same thing. This is for a black hole source. Okay, that is XTEJ 1550. This is a black hole source. You can see these are the quasi-periodic oscillations. So we use these quasi-periodic oscillations in order to know the nature of the compact object. So this is another kilohertz QPOs which I shown you. So these are twin kilohertz QPOs. So there is a fundamental frequency, there is a secondary component, and this is for another source. This is again some QPOs from black hole binaries. This is the evolution. So as the X-ray count rate increases for a black hole, you can see that the QPO frequencies gradually increases. This is the frequency plot. This is the QPO frequency. It saturates, and as the X-ray count decreases, the QPO frequency come down. So these are important in order to understand the behavior of the matter around the black holes. This is the comparison between a black hole. This left side is for black hole QPOs and the right side is for neutron star QPOs. So you can see that these are again classifications which I don't go about. Just for a relative comparison, I have kept it here. So this is one of my research. I used one NASA-based satellite. This is one of the X-ray variation. You can see a constant variation with a sudden dip. Okay. So during the constant variation, I can see a QPO feature, and suddenly it disappeared when there was a dip. So we try to explain that some of the part of the accretion disk has been ejected by the black holes. So these accretion ejection triggering mechanisms are not very clear with the black holes. That's why these results are very, very important. Again, I've continued these studies for other sources, that is XTEJ 1859. Again, we can see that in these variations, here you find a QPO, that is this, and suddenly it went somewhat quiet. There's not much fluctuation, so there was no QPOs. So we used various spectral tools in order to understand what component of the spectrum is actually disappearing and why it is happening. So this is quite a normal phenomena in this particular source. So this is with another black hole source. He's my PhD student. He carried out these studies. Yeah. So this is my recent work, 2022, where we were studying two different types of QPOs, but at the same frequency, at 6 hertz. So at same frequency, you should not see two different type of QPOs. So there is some mechanism which is occurring at this scenario. So we studied, we took a sample, and we found that among 23 observations, there were 9 type C QPOs and 14 type B QPOs, and we studied we used a spectral model and tried to find out what is actually causing this, what is the difference between them. So we found that in type C QPOs, the disk temperature is less than keV, and hard flux is always greater than soft flux. Whereas it is in type B QPOs, they are actually opposite. So the disk temperature is very, very hot, more than 1 keV, and power law index is smaller compared to this thing. And what we found out in type C QPOs, the inner region is very much spherical in nature, whereas in type B QPOs, it is elongated vertically along the spin axis of the black hole. So we said that it is basically connected to the jet, which is also supported by radio observations. So yeah, so what we found is, this is very interesting result in type B QPOs. We found that the width of the QPO, which I have shown you, the width of the QPO is, this is FWHM, that is the width of the QPO is connected to the radio flux. So somehow these QPOs are affected by the jets, and that jets are basically detected in radio wavelength. So we use the radio flux density and try to correlate, and you can see a very, there is a linear regression going on. So we say that type B QPOs are very much related or very closely associated with the jet components. This plot is interesting one. This is for the same source. This is, we say, dynamical power density spectrum. Basically, dynamical power density spectrum means with respect to time, if you want to study the power density spectrum, this is a type C QPO, and suddenly after some 20 hours time scale, it suddenly changed to type B QPO. So we say that there is a ejection happened, accretion disk ejection happened at this place. And when we studied the literature, we found that radio observation shows that there is actually a radio ejection happening there. So what we're trying to do is we are trying to correlate the X-ray features and the radio features, whether they are tight up or not, in order to get a unified model. This is AstroSat, India's first, not first, second, actually it's a second X-ray mission. First it happened in 1997, it worked for 2 years. But multi-wavelength studies, this is the first X-ray mission. And these are different, see this is UVIT, ultraviolet imaging. This is cadmium zinc telluride. These three red boxes are basically LAX PC. And this is very, and there is another, this is the SXT telescope, okay? This is soft X-ray telescope. This is one of my research scholars. This is the neutron star SXT image from AstroSat satellite, and where we studied the timing as well as the spectral features. This is the X-ray variation. You can see that as the intensity is varying of this source, you can see that the timing properties also varies, and as well as the spectrum also changes. This is one of the simulations result. I'll just skip it out. Yeah. So young researchers, PhD students or master students, whoever is there. So take home, if you are doing observational astrophysics, you have to have a good data. You have to reduce it. You have to analyze it, whether it is a timing, whether it is spectrum, whether it is a polarimetric. If needed, you have to robust your results by doing simulations, Monte Carlo simulations, or using random number generators. And we have to use these results in order to constrain some astrophysical property about that source. This is what happens in observation astronomy. Okay. And one should know that in observation astronomy, you have to do computations, you have to perform simulations. It is not doing research like 10 years back when I used to do. There was the significance was, simulation people used to do very less, but nowadays, if you need to have publication, you have to perform simulations. Otherwise, it's very difficult to accept your paper. Okay, I do a lot of cross correlation function analysis and error estimates. So there is only one advice which I would like to give to the youngsters. Whatever physics or maths you are learning, you have to connect it to your computers. You have to able to write, you should able to write the codes. Let me tell you, otherwise you are not going to get any project grants or postdocs or something. One of my students, she has completed her PhD, she moved to US for postdoc. Her job is to write codes. Every day she is writing codes on Python or whatever you are using, machine learning, AIs. You have to convert your read physics, maths, what you have done, derivations, etc. You have to write in form of codes. If you can do that, let me tell you, you can attract the projects, you can get PhD seats, you can get postdocs, you can get whatever positions you want. Okay, that is a piece of advice which I would like to give it to you. Yeah, so this is, so you can, anybody who is interested in doing X-ray observations, X-ray studies, these are the data. Indian X-ray Space Observatory is AstroSat. XpoSat is recently launched and we are getting the data right now. And these are all New Star, NICER, NASA mission, ESA missions. And these are RxT, Suzuka, you have plenty of archival data. Thank you. All the best, thank you.
Do we have any questions?
Just take spherically symmetric ones or even ellipsoidal or triaxial triaxial. And well, for ellipticity, to what extent can we go? Say if zero is perfectly spherical, so to all the way till one. But that will be a highly disky then. Yeah. For neutron stars, how far can we go? Okay. And wobble of a neutron star is taken for understanding the light curves and or
Now let's move on to the next part of our session, the oral presentation segment. We have 6 presentations and we'll follow the same order which is given in the schedule. So first we'll have Dr. Priya Hassan's presentation, which is offline, and then the next presentation would be by Dr. Aisha Anjum. Please be ready with your presentation. It's an online presentation, so please be ready with your presentation. So I would like to request our first presenter, Dr. Priya Hassan. Priya ma'am.
Thank you. Yeah, so thank you. Thanks, Sriram, for that great talk. Where are you? Oh, he's here. Ah, you're chairing. Ah, yes, okay, okay. Great. Yeah, so thanks so much. So, initially I thought there won't be many talks on astronomy, so I thought I should take up something which is, more, more, which is more attractive to people. And that's why I've taken up something on when will Betelgeuse go supernova. Okay. So, yeah. So many of you all may know this constellation. This is Orion, right? In winter, you would have seen this. And this is the right-hand corner of Orion, where there's a red giant star, which is called Betelgeuse. And that's the star we are actually talking about just now, right? So uh, there's a paper which I've written on this, which is there in Resonance. You can have a look at that too. So that's Betelgeuse. Again, if you know this constellation, Orion, the three, this thing, and Betelgeuse is here, right? So once again, that's another picture of Betelgeuse. So what is Betelgeuse? Betelgeuse is basically a red giant star, which is at a distance of approximately 200 parsecs. It has an age of about 8.5 million years. And its progenitor mass, it should have started off with a star of about 20 times the mass of the sun. And it rotates around every 8.55 years. Now, what's the fun part about Betelgeuse? Why are people so interested in Betelgeuse? So first of all, Betelgeuse is a variable star. That's because it's not sitting on what is called the main sequence. It is off the main sequence. And that's when stars basically are unstable and they are variable. So Betelgeuse is one such variable star. And they are typically various pulsations, which is at basically 4 periods, 2,200 days, 420 days, 230 days, and 185 days. There are 4 periods sitting in there. And what happens is, why do these stars pulsate? That's basically because you have nuclear reactions taking place in the star. This is when it's moved away from the main sequence. So the core from hydrogen has already become helium, and then from helium you're fusing heavier and heavier elements. So what happens is, as the nuclear processes take place, the star swells up. The star swells up, it cools down, so then the nuclear reactions reduce, so then it kind of collapses. And then when it collapses again, it gets heated up, and again you have nuclear reactions, and the star swells up again. So that's how you have, these are called pulsating stars, and that's how these guys pulsate with various periods, which I have mentioned. So that's normal, no problem. Then why the noise? So what happened in October 2019 is this star is about the 10th brightest in the sky. Okay, the 10th, 11th brightest. And in October, since October 2019, it suddenly began to dim. Okay, the star began to dim and it kept on dimming till by March 2020, etc. It actually fell down by a factor of about two and a half to three times its normal brightness. And suddenly from the 10th or the 11th brightest star, it became the 21st, right? So suddenly the star became very faint, okay? So you can't see these pictures to where we need to switch off these lights. These lights. So you can't see it, but in short, the star did get very dim. So if it looks dim, it's that's what happened. Now, obviously, so you had Betelgeuse like that, and suddenly it was getting dull. So people wondered, oh God, does this mean we know it's a red giant, so it's now heading on to become a supernova. So people thought this is the lull before the storm, and that's how the star has dimmed, and now suddenly the star is like going to go boom, right? So people were very, very excited. So you have the luminosity, and you know the luminosity of the star is basically 4 pi r squared into sigma t power 4, right? So either the star is cooling down, so the luminosity is falling, or something like that, which is causing this process. But I'll just do a small, very small thing. What basically happens at stars? This is a ball of gas, which basically you basically have nuclear fusion taking place at the center, and it's held together by gravity. But in stars, mass is a very important factor. So typically what happens if a star is a low mass star, like the sun, for example, it'll become a red giant, a planetary nebula, you'd be left with a white dwarf, and so you'll have the white dwarf in the center and the planetary nebula outside, right? If it's a massive star, like Betelgeuse, for example, which has a progenitor mass of 20 times the mass of the sun, then such a star is going to become a supernova, a type 2 supernova, and then depending on its mass, it either ends up as a neutron star or a black hole, right? So that's the typical kind of sequence which we expect. So, yeah, that's the same thing. Now, supernovae in general, we know that galaxies like the Milky Way, you approximately have 3 supernovae per century which take place. So they're not very often. It's something to look forward to. And the last one you know very well is what is called Kepler star, which was seen in 1604. And it was bright enough to be actually seen in daylight. You had Cassia, we won't go into more details. But back to Betelgeuse. Now, Betelgeuse, one of the theories as to why did it dim was that there's what is called episodic mass loss. Okay, so this is basically coming from this image, which is a VLT image, which is in the infrared. Now, infrared, you can see gas and dust very well. So what was seen actually in this image of Betelgeuse is that there's a large amount of gas and dust around the star, right? And Betelgeuse in the center, and therefore the theory for what happened, this is various observations have put into this as to why did the dimming basically take place. This is the dimming, and the idea was that probably the star just threw out a dust cloud which came in front and got the star so dim, right? And then this was not the end of the surprise. Finally, what happened? This is 2020, and now you can see over here we are 2023, January. You see that gradually after this thing which is called the Great Dimming, you suddenly had Betelgeuse again recovering, right? So again it increased up in its brightness. So by January 2023, it was like slightly even brighter, 50% brighter than it would normally is, right? So this theory which we had of this gas cloud coming in, which actually did it. So the most prominent period is a 400-year period. But now obviously the star has got totally, it's in a messed up condition. So you have this period totally being violated, and it will take some time to actually get back to its period. At present, it's off the period. And then you had various observations from various telescopes which actually followed up the idea of this gas dust cloud. And then a very interesting paper came out last year, which is a very interesting paper that we know that this red giant is going to fuse. The helium will fuse to carbon, carbon will fuse to silicon, neon, various other heavier and heavier elements. And what these people did, this group, is that they used the data for Betelgeuse because it is being monitored very well. They actually studied the light curve and the pulsations taking place to show that Betelgeuse is already in the last stage of carbon burning. Now, if Betelgeuse is on to carbon burning, then within 100 years or within a few decades, it's going to go supernova. Okay? So this paper was actually accepted also. So it's already published also in MNRAS, where they now expect Betelgeuse to be, in a century or a few decades, right? So they use this radial velocity data which they had from there, as well as the variation in the magnitudes, and they actually could even explain the great dimming which was there. They could explain that also to explain the light curves and see the composition of the core. Now, obviously, this is a very tricky question because to know what's actually happening in the core of a star is a very tough thing, right? So you are model dependent, and there are many reasons why your model could actually, make mistake. I mean, go wrong. So there's been even a rebuttal on the paper. In the paper, they basically used that 2,200 year period, which is 2190. They took it as the fundamental frequency, and there were certain objections to the paper as to whether this is actually true. We don't have the time to talk about it, so I will not. But Betelgeuse again is behaving in a strange way. It's pulsating twice as fast. That 400-year period has become a 200-year period. It's glowing at about 150% of its usual brightness. And the most interesting part about it is that, like I told you, Betelgeuse is at a distance of about 600 light years, okay, 200 parsecs. So if there's even a possibility that Betelgeuse has already gone supernova, right? Because the distance is something between 600 to 800 light years, right? So if the paper I mentioned is right, and Betelgeuse already was ready to go supernova, right, within a century or a decade, then it probably already did, but the light has not yet reached us. So for all you know, while we are so worried about Betelgeuse going supernova, probably it already has. The light has still got to reach us, and it's on its way. So though we are watching it in the past, the light could be, maybe it's already happened. We do not know. But I'll just end with, what if Betelgeuse actually went boom? Okay. So actually it's quite far away from us, 600 light years, nothing much to worry about. So therefore, but obviously it will be bright enough that you'll see it for the whole week. You'll probably see it. It will be bright in the day. You'll see shadows caused by it. But obviously the shock wave, it will almost take 6 into 10 past 6, a million years to actually reach us, right? Though it's moving at 13 kilometers per second, it will stop outside the Earth's orbit. So in short, we are protected. The killer zone for a supernova is actually 10 parsecs. If a supernova happens within 10 parsecs, that is something to worry about. So Betelgeuse is nothing much to worry about. So I'll end with this, that we are safe, and even if Betelgeuse does go supernova, we are fine. Or maybe if it already has, that's also a possibility. Yeah. So I'll end with this, and thanks.
Thank you, madam, for giving a nice talk on the source Betelgeuse. We have a time for one question. Anybody want to ask one question? Yeah. If it is not the case, let us again applause for our speaker. And let us move on to our next speaker, Dr. Aisha Anju. She will be giving a talk on revisiting PKS 1502 plus 036 and PMNJ0948 in MIR mid-infrared wavelength bands. Anjum is she's online, so you can see her talk.
Am I audible now? Okay. Can I share my screen? That visible now? No. Is that visible? Please confirm. Thank you. So, my name is Aisha. I'm from SDC College from Kolar. And first of all, I thank everyone, the whole committee and the organizers for giving me an opportunity to talk here. And the topic of today is, as I said, it is revisiting these two objects. These two objects are basically Seyfert galaxies. keeping in mind that students are there among the audience and the diverse in people with diverse interests, I would like to first tell what are the objects about. So first of all of you know what are galaxies. These galaxies are just they are bound systems of stars and gas and other dust, and mainly these are the gravitationally bound systems. The sizes of these galaxies can range from very small galaxies having a few thousands of stars, or it may be as large as having hundreds of stars and all that. All galaxies do have supermassive black holes at their center, but the difference between galaxies is that some galaxies have only black holes which are inactive and they do not have accretion disk around it. But there are some galaxies which have supermassive black holes which are actively accreting matter around them, and also they have accretion disk around. Okay, so these are the two types.
Aisha?
Yes, sir.
Yeah, please continue.
Okay. Audible, no, sir?
Yes,
Okay.
audible.
All right. So, in case of normal galaxies, they do follow Hubble classification. It's like they have there are elliptical galaxies and there are spiral galaxies and barred spiral, all these things. Their luminosity is very, very less. And also the basic source of energy production in these objects is just fusion. And they emit thermal radiation. Now, these are few examples of normal galaxies. They are basically extended objects which could be very far away or very near to it. So these are the barred spiral galaxies, spiral galaxies. These are irregular in shape, and these are elliptical galaxies. These are lenticular galaxies, regular galaxies, different shapes and all that. Now coming to active galaxies, as I told you, these galaxies have a supermassive black hole at the center, as you can see over here, and surrounding it, there's a lot of matter which is being accreted. That matter is moving with relativistic speeds, if possible, around it. Okay, and this is a jet wherein you have electrons and charged particles moving with relativistic speeds. That is why it is called as relativistic jet. And these are very far away objects. When the objects are very far away, it's very hard for us to see. But then the luminosity of these objects is so great that even though they are very far away, we can see them. But we can see them as just point objects, not extended objects. Okay, so the luminosity is of the order of 10 to the power of 11 or 15 solar luminosity. And the main energy production mechanism here is accretion. And they emit in mostly non-thermal radiation. They emit non-thermal radiation all the way from gamma rays to radio waves. They produce everything, all kinds of radiation. Now, the title says that we are studying these two separate galaxies in mid-infrared bands. Why so? Why not in other bands? And why? What is the importance of studying it in different bands? It is because this is the same object that you can see, but these objects are observed in different wavelength bands. Like if you are observing it in X-rays, it looks like this, completely different from what you see in UV, completely different in optical. It's like that. So when you merge all these 6 images, you see an image of someone like that. So you won't be able to judge the object just by observing it in only one wavelength band. Not only in case of wavelength bands, it also depends on at what angle you are observing it. Suppose you are observing it face on, then it looks like a blazar. You can see over here. If you are observing it edge on through the, see, this is a torus. Okay, and at the center there is a black hole. Surrounding it, matter is accreting with high speeds. Surrounding it, you have dusty torus, like you have a lot of dust in that which can absorb optical radiation and all that. Okay, so there you have narrow line region and broad line region. This is the morphology of a active galactic nuclei, which is proposed by Urey and Fedovani long back in 1995. Okay, so what we are interested in is this Seyfert 1 type of galaxy. So we're observing at this object in this angle. So that is what we are studying now. Now there is something called variability. What is this variability? Like any object which produces radiation of different kinds, that radiation will not have always the same intensity. It has to vary. Why is it? It should be based on the production of that radiation, the site of production of that radiation. It can be starting from, within the torus, dusty torus, or the photons which are produced in the accretion disk. They can go hit the dusty torus and get reprocessed, and they can get re-emitted in IR or some other band. It is also possible that there is something called seed photons. The meaning of seed photons is that the photons are emitted from somewhere else, within the AGN, and they go hit the relativistic electrons which are there in the jet. They undergo inverse Compton, and then they are irradiated back, maybe in IR or something. Okay, so this variability depends on from where the radiation is being produced, or from where is it getting re-radiated, or from where it is getting reflected. Okay, so that is the main thing about variability. Now, the data for this work is taken from WISE, Wide Field Infrared Survey Explorer. The importance of taking data from WISE or IR, infrared or mid-infrared bands is that because of the presence of torus, all the optical radiation that is coming from the center will be absorbed, whereas the IR won't be, the torus won't be able to stop IR. Right, so that is why we are observing using this one. Now we are observing in 4 wavelength bands, that is in W1, W2. The wavelengths are given here, 3.4 to 22 micrometer bands. This goes into hibernation. WISE, the telescope goes into hibernation, and then it comes back, and it is started again, recommissioned to observe near Earth objects, and it is given as new WISE and all that. I don't want to elaborate on that. I just want to skip this slide. We have taken data from here. These are the light curves that we have built for the 2 sources, that is PKS1502 plus 036, and that it is, the data is between the years 2014 and 2022, I think, so for over 8 years. So this is the data that we have used. To ensure that the data, the quality of the data, we have made sure that chi-square per degree of freedom is less than 5, and its PSF should be PSF should be less than 3, and should be the number of data points that should be used for our analysis is less. It should be minimum 4. Okay, we have taken in each epoch, we have taken at least 4 data points for the analysis. We have also used data from Fermi Large Area Telescope Light Curve Repository, and the data here is bent at 3 days, and the details of the telescope I'm going to skip it. Now the analysis is based on the equations given by Fisher et al. In 2007. We are actually finding out the amplitude variability. Since the amplitude of variability also depends on the errors in the observation, we have used both the observed errors as well as systematic errors or uncertainties in the observation. Okay, epsilon I is the observed error or uncertainty. Epsilon S is the systematic uncertainty. So using this, we have found out the amplitude variability of both sources in each epoch. Okay. These are the data. This is the data that is taken from Fermi, and the light. This we have built a DCF, discrete correlation function, to check whether the correlation is there between the mid-IR bands, WISE bands, as well as the Fermi bands. We saw that there is no correlation between these 2 bands. Okay, now So these are the color magnitude diagrams. Along x-axis, we plotted the magnitude W1 and W1 minus W2 gives out as the color. So what is this trend? Why is it important? Is because there are two trends basically: bluer when brighter band or trend, or redder when brighter trend. When I say bluer when brighter, when the object becomes brighter in any one of the wave bands, it becomes bluer. Like it may be possible that the radiation is which is coming from the external disk is very bright compared to the central region. That's how it becomes brighter. So in case of Seyfert galaxies, both Seyfert galaxies, we are getting a positive trend, that is bluer when brighter trend. I'll just tell you in a minute what this means. Now, only in one of the epochs, we got that the trend is negative, that is, it is showing redder when brighter trend. So this is related to PKS and PMN, the two sources. Both sources are mostly brighter and bluer when brighter. So when can it be bluer when brighter is because the spectral hardening, because of the spectral hardening. The bluing of the source is followed by brightening of the variable component. Like when it becomes brighter, it will become bluer and all that. So opposite is in case of redder when brighter trend. Looking at the duty cycle of these objects.
Aisha, I think your time is up. Priya Madam has already given 1 minute time.
Yes.
Can you just quickly conclude your talk?
I'll conclude, sir. I'll conclude. So the conclusion of the discussion is that Seyfert galaxies are believed to be the hosts of the Seyfert galaxies are believed to be spiral galaxies. But when we look at the variability of these galaxies, it is similar to the blazars. And blazars are like, they are hosted in elliptical galaxies. So this is the conclusion. And using variability, they look like old elliptical galaxy types. Looking at their morphology, they look like spiral galaxies. So it is difficult for us to come to a conclusion that these are the predecessors of, like, they have evolved from old elliptical type galaxies to the Seyfert galaxies. So we are looking at more number of objects so that we can come to a conclusion about the evolution of these galaxies. So that is the conclusion.
Yeah, thank you, Dr. Aisha. We can have a quick one question if anybody is having any question. The question is how you have studied the morphology of these galaxies?
We have understood it from the previous lecture, like from literature, previous literature.
From the literature, sir?
Yes.
No.
It is not my work.
Some other paper, they might have reported all this thing.
Right. So how do you understand the morphology of this one? It could be using reverberation mapping, or in other wavelength bands. If they study, it will be possible to understand the morphology. They do build models regarding how the structure is.
Okay, Aisha. Thank you, Aisha. Yeah, let us move on to our next talk by Harsha Sri Kumar. The talk title is Evolution of the Universe in Kappa Deformed Spacetime.
So, hi, I'm Harsha Srikumar from University of Hyderabad, working under Professor Hari Kumar. I would like to thank Rizwan sir and the university for this opportunity. The talk is on evolution of universe in kappa deformed spacetime, and this is the outline of my talk. To introduce you to the talk, usually the origin and evolution of the universe is studied under the framework of general relativity. But in 1934, E.A. Milne and W.H. McCrea showed that the governing equations of general relativity can be constructed using Newtonian dynamics. They showed that for galaxies that are close to each other, moving with low relative velocities, the locally observable phenomena remain identical while formulating it using Newtonian dynamics, and hence it is simpler to work with Newtonian cosmology for such cases, as the mathematics is also simpler. So in our study, we have considered the universe to be of the form of sphere with mass capital M and radius r, and we have considered a distant accelerating galaxy on the surface of the universe. The mass of the universe is assumed to be concentrated at the center, and the force of attraction between the universe and the galaxy is that of Newtonian gravitation. Yeah. So to introduce you on non-commutative spacetime, the quantum study on quantum gravity is still an unsolved mystery in physics, and there are various theories to study quantum gravity, like string theory, loop quantum gravity, causal sets, non-commutative geometry, etc. And all these approaches incorporate a fundamental length scale beyond which these quantum gravity effects are expected to be seen. And non-commutative geometry is one theory where this fundamental length scale is incorporated naturally. Hence, it is of interest to study phenomena in non-commutative geometry. Some examples of non-commutative spacetimes are DFR spacetime and kappa deformed spacetime. To introduce you on kappa deformed spacetime, in kappa deformed spacetime, the coordinates satisfy the commutation relation given by equation 1, where A is the deformation parameter with the dimension of length. And there are various approaches to study phenomena in kappa deformed spacetime, but we have used the realization approach, where the non-commutative variables are written in terms of commutative variables and its derivatives. We have used two different realization in the paper, namely warfare realization and alpha beta gamma realization. I'll be discussing the results of only warfare realization. The results of alpha beta gamma realizations are fairly similar. So in warfare realization, the kappa deformed coordinates can be written in form of equation 2, where capital A is minus AP0 and psi, gamma and warfare are functions of A. And the free particle dispersion relation in kappa deformed spacetime can be written as in equation 3. So to go to a system where we had considered a spherical universe with radius capital R and mass capital M, with a distant accelerating galaxy on the surface with mass small m, the total energy of the galaxy can be written as seen in equation 4, where A-dependent terms are the non-commutative corrections. And incorporating this mass of the universe into this equation and redefining some quantities where 1 by r dr by dt is defined as h, which is the Hubble parameter, and k to be minus 2e by m r cat square, which can take values 1, 0, minus 1, where r cap of p1 is the radius of the universe at time p1. We get the first modified Friedmann equation as seen in equation 6. And using the first law of thermodynamics, where the heat transfer is taken to be 0, and we get the continuity equation of the form of equation 7. So using this continuity equation and the first modified Friedmann equation, we can formulate the second modified Friedmann equation valid up to first order in deformation parameter A. So now to see the effects of non-commutativity on the scale factor, we consider the equation of state given by P equal to gamma minus 1 rho, where gamma is a constant, and substituting this onto the continuity equation, we get the equation given by equation 9, where rho 0 is the energy density of the universe at the present time, and r0 is the present radius of the universe. So incorporating this onto the first modified Friedmann equation and taking k to be 0, we get the time evolution of the universe for radiation dominated, matter dominated and vacuum energy dominated universe. So in case of radiation dominated universe, we take gamma equal to 4 by 3 and taking k to be 0, the first modified Friedmann equation takes the form as in equation 10, where A is the scale factor given by R by R0. Solving this equation, we get the value of A to be this, and where these A dependent terms are the non-commutative corrections, and tau is defined to be root of 8 pi g rho 0 by 3 t minus t0. Now we plot this A versus tau graph taking the mass of the galaxy to be that of the Andromeda galaxy and P0 to be the mass of an extragalactic black hole. So plotting the variation of scale factor with respect to tau, we see that this black line corresponds to the commutative case, and this orange dotted line and red dotted line corresponds to the non-commutative case, taking the deformation parameter A to be positive. So we see that the contraction and expansion of the universe is slower compared to the commutative case where A is positive, and this green and blue dotted lines correspond to the case where A is taken to be negative. So for negative value of A, we see that the contraction and expansion of the universe are faster compared to the commutative case. So there is a puzzle in the field of cosmology called the Hubble tension, which is a discrepancy observed in the value of Hubble parameter. So looking at the Planck data, we have the value of Hubble constant to be around 67 km per second per megaparsec. And looking at the supernova data, we have the value of Hubble constant to be around 70 km per second per megaparsec. So our results indicate that depending upon the value, sign of the deformation parameter, the evolution of the universe is different. So this variation Hubble constant could be because the results, the measurement of the results of the measurement may be because the measurements are sensitive to only certain type of quantum gravity corrections, which is why we could be seeing this difference in the Hubble parameter constant. So if a measurement is sensitive to all kinds of quantum gravity corrections, maybe this discrepancy in the Hubble parameter could be resolved. So next we consider matter-dominated universe, where we take gamma to be 1 and k to be 0. We get the solution to the first modified Friedmann equation of the form of 12, where A-dependent terms are the non-commutative corrections. Plotting this, we get a similar graph where the orange and red dotted lines represent to the case where A is taken to be positive. So we see that the contraction and expansion of the universe is slower compared to the commutative case, and green and blue dotted lines are cases where A is taken to be negative. So for negative value of the deformation parameter, the contraction and expansion of the universe is greater compared to the commutative case. Similarly, we study for vacuum or energy dominated universe where gamma is taken to be 0 and the solution is as seen in equation 13, and plotting it, we get this graph where as in previous cases, the black curve corresponds to the commutative case, the orange and red curve corresponds to the case where A is taken to be positive and the contraction and expansion is slower compared to the commutative case, and the green and blue dotted lines are cases where A is taken to be negative and the contraction and expansion of the universe is faster compared to the commutative case. So to conclude my talk, in kappa-deformed spacetime under the framework of Newtonian cosmology, we have derived the modified Friedmann equations, and using the Friedmann equations, we have found the evolution of the universe for a radiation-dominated, matter-dominated, and vacuum-dominated universe. And the evolution for both the evolution of the universe is similar for both the realizations, which is why I have not shown the results for alpha, beta, gamma realization. And this difference of the evolution of the universe, depending upon the sign of the deformation constant, could be a possible explanation for the Hubble tension. And we got a bound on the deformation parameter A to be around 10 to the power minus 85 meter. And in non-commutative spacetime, there is an uncertainty relation which indicates a minimum volume to the universe, which indicates a bouncing universe rather than the singularity that is widely expected. These are the references. Thank you.
Thank you, Harsha, for a nice talk. Any question? Any question?
Which seeks to be best for what? No, the present observations show both the value of the Hubble tension. They show some of the observations show the Hubble constant. No, we cannot say which model will be closer to that. We are just saying that if all the quantum, we have seen in our case that depending upon the deformation parameter, there is a variation in the evolution of the universe. If all the quantum gravity corrections other than in all the quantum gravity correction, apart from this also, if it is incorporated, this discrepancy in the Hubble tension may be resolved. It's not for sure. Yes, sir. No, sir. But sir, we are in Newtonian cosmology, we are considering only two distant galaxies which are close to each other. Newtonian cosmology is relevant only in that cases where universe is almost flat and the galaxies are close to each other and they're moving with low relative velocity.
Consider dark matter for these models, what you're using, comparative. People have studied, right. Okay, Archana, thank you. Nice talk. Okay, let us move on to our next talk. Next speaker, Suman Kumar Panja, and his title is Neutron Star in the Presence of Minimum Length Scale. Hello. Hello. So I'm Sunil Kumar Panja. I am doing PhD under Professor E. Hari Kumar in University of Hyderabad. So in this talk, I'll talk about Newton's star in presence of the minimal length scale. This is the outline of my talk. So in previous talk, in ma'am's talk, we have already seen that life cycle of a star. I just want to tell, when massive star collapse, it eventually results in the supernova explosion. And from the remnant of the supernova explosion, we get superdense stars such as this Neutron star, white dwarf, black holes. Most of these superdense stars have the core density of 10 to the power minus 17 kg per meter cube, and the radius is order of 10 to the power 4 meter. And so far, various studies have been done to find the mass and radius of a Neutron star. And from observations in this article, it is argued that from observations of this gravitational wave, this mass of the Neutron star is 2 with 3.4 solar mass. Also, parallelly, different theoretical models have been studied, and there the maximum upper bound on a mass of a Neutron star is found to be 3.575 the solar mass. In all these theoretical models, an important point is that TOV equations and equations of states are used. Okay. So it is expected that gravitational force near this superdense star is very high, and for that we can expect that it will provide a natural laboratory to test these quantum gravity models. What I am meaning by quantum gravity models is that to understand the gravity at a Planck length scale, we need different kind of models. Some are this string theory, loose quantum gravity, emergent gravity. One of the most well-studied quantum gravity model is this non-commutative geometry. All these quantum gravity models introduce a fundamental length scale in the theory. Non-commutative geometry not only introduce fundamental length scale, it also
provides pathway to incorporate this fundamental length scale in the theory naturally. So one of the well-studied non-commutative spacetime is null spacetime, where coordinates satisfy this commutation relation. Another well-studied non-commutative spacetime is kappa spacetime, where the coordinates satisfy this commutation relation given in equation number 2. Here A is the deformation parameter which has dimension of length, and the corresponding symmetry algebra of this spacetime is kappa deformed Poincare algebra. Non-commutative spacetime also appears in the low energy limit of other quantum gravity models. So far we have seen that non-commutative geometry inherently encodes this length scale and provide a path to incorporate the fundamental length scale in the theory, so that we can study different quantum phenomena as a background. And also we have seen that TOV equations and equations of states are used to study this Newton star model, which is expected to be modified in non-commutative spacetime. So that is why our interest to study this Newton star model in non-commutative spacetime. In this study, we have used the kappa deformed spacetime as a non-commutative spacetime, and we have constructed and analyzed this Newton star model in kappa deformed spacetime. So this part already my previous speaker has been already told, so I am just skipping this part. So generic form of the pre-particle dispersion relation in kappa deformed spacetime is given in equation number 8. So for this case, but we are using this particular realization. So where phi to be e to the power minus 3, and then our dispersion relation will become like this, and the energy momentum relation will become like this. Okay. So next, I'll talk about the deformation of metric in kappa deformed spacetime. In kappa deformed spacetime, phase space momenta commutation relation can be written as the equation number 12. And one can realize this phase space coordinate as the equation number 13. So for specific realization from this equation, for specific realization from that commutation relation, we can get equation number 15, and we can find the kappa deformed components of the metric, where this highlighted part are the modification which is coming due to non-commutativity of space-time. Also, we found what will be the line element in kappa deformed spacetime, which is given in equation number 17. So as we will study the we will construct the Newton star model in kappa deformed spacetime. The line element for the metric is given in equation number 18. Using this in equation 17, we found this kappa deformed spacetime metric for Newton star. Also from the energy momentum relation, we found this relation, and then we start with the kappa deformed generalized energy momentum tensor. Using these two, we found this energy, this density expression and the pressure expression for perfect fluid model. Here we have considered that interior of the Newton star to be a perfect fluid, and thus we found out this components of energy momentum tensor, which has this deformation correction, which is given equation number 26. Also using this energy momentum tensor expression or components and the kappa deformed metric, we found from the Einstein field equation, we found this TOV equation, which is given in equation number 28, 29 and 30. Next, we have considered that exterior of the Newton star to be kappa deformed Schwarzschild, and for that, now this is the line element, which is given in equation number 31. Using this, we have solved that TOV equation explicitly. Also for that, we have used this strong energy condition and space-time causality condition. and we found the radius of a neutron star and the mass of a neutron star, which is getting deformed due to non-commutativity. Also, we have found the compactness factor and the surface redshift for the neutron star. Here, interesting point is that there is no modification is coming in the this compactness factor and the this surface redshift. So now, if we do the numerical analysis by taking this correction part to be 0.01, which is by taking P0 to be 10 to the power 6 m naught, which is mass of a black hole. Then if we change the radius of a neutron star, we can see that mass of a neutron star is also increasing with the radius of a neutron star, and also compactness and the surface redshift also increasing. Also from this analysis, we found the upper bound on the neutron star mass is 3.6805 solar mass. And if we plot this analysis or this, okay, and then we will get this mass radius plot, where we can see that at a higher radius there is a deviation in the commutative case and the non-commutative case, which is obviously it is because of non-commutative of the non-commutativity of the space-time. And also from the observational value of the neutron star mass, we have found the deformation around 10 to the minus 44 meter. So from this study, we have seen that upper bound on the mass of a neutron star is getting enhanced. Also, for fixed value of deformation parameter, mass is increasing as radius is increasing. Compactness and surface redshift is showing same nature with the this radius of a neutron star. Also, we have from the observational result, we have found the upper bound on a mass of a neutron star, and also we have found the deformation parameter to be 10 to the minus 44 meter. So these are the reference we have used. For more calculation details, you can see this paper. Thank you.
Thanks, Suman. We have time for one quick question. I have one small question. You wrote minimum mass is 0.26, but Chandrasekhar mass limit is 1.4. That's for white dwarf. So, because changing the analyzing the mass. Okay. We are not telling that that is the lower limit. Okay. Radius decreases.
Yes, it is. We are showing now. When we are increasing the radius, mass is increasing.
But it should be opposite. As mass increases, the radius should increase.
No, in this case, we are seeing.
Yes. As you increase the mass, the radius decreases.
For this case, we are seeing that
it is increasing. Okay. Okay.
Let us. Deformation parameter is coming as a plus.
Plus term.
So
it will increase. Okay. Anyhow, let us thank the speaker. Let us welcome next speaker, Deblina Lahari, and her talk is X-ray reverberation lags in an AGN Markarian 704.
Good afternoon, everyone. I'm Deblina. I'm research scholar at the Department of Astronomy, Osmania University. I work under the supervision of Dr. K. Sriram. My topic is X-ray reverberation lag in AGN source Markarian 704. So this is the outline of my talk. The image that you can see on the right side is the X-ray image of this particular source taken from XM Newton satellite. So for the introduction, we all know that all the galaxies in the universe has a supermassive black hole at its center, and it is ordinary galaxy configuration. But there are certain galaxies in which the central region is very bright, as it has a supermassive black hole and it is not inactive, it is active. It has accretion disk around it, and and hence as this central region of this galaxies are so much active, they are known as activating nuclei or AGN. Okay, so briefly I will go through the different components of AGN. First is the supermassive black hole. It is almost billion to million times the mass of the sun. Then comes the accretion disk. You can see this red and red line here. These are the disk. This disk mainly radiates in optical and UV, but the innermost region of the disk radiates in X-ray, and that is what my study goes with. Then comes the corona that gives off the hard X-ray photons from there. Then comes the BLR cloud. It is optically thick cloud. They have high velocity. They are located at a place at a distance of 1.1 to 1 parsec from the supermassive black hole. They have a few thousands of kilometers of velocity. Then comes the dusty torus here. It actually covers the whole radiating part, the supermassive black hole, its disk, along with the corona. Then comes something called the NLR region, the narrow line region. These are also clouds like BLR clouds, but they are optically thin and they have much lesser velocity, few hundred kilometers per second. Then there is relativistic jets, collimated beams coming from the base of the corona. We exactly don't know how from where it is coming, and it is sometimes present in certain regions and sometimes not present. Okay, so this is my source, Markadian 704. We have used European Space Agency's XMM Newton satellite. It has basically three important EPIC cameras, MOS1, MOS2, and PN. My work is with the EPIC data, EPIC PN data. So this particular source has been observed by the XMM Newton satellite on two occasions, one in the year 2005 and next one is in the year 2008. And we have found that there is a 40% difference in the X-ray flux among these two observations, and that is the important reason why we are studying this. So now I will be briefly explaining the concept of time lag that is very important for this talk. Let us consider here this black dot as the black hole. This orange thing is the disk, accretion disk, and here the red is the X-ray emitting source, corona, at certain height. So now what happens? The hard X-rays means the X-rays having energy more than 2 keV. So those hard X-rays, some part of this X-ray comes to the observers, and some part of it gets down scattered. It falls on the disk, and it produces soft X-ray photons. X-ray photons having energies from zero point 0.3 to 1.5 keV. And as it is down scattering and falling, it looks like something like a reflection. Hence, we call this as a reflection model. Now, as these two photons, like hard X-ray photons and the soft X-ray photons, have a difference in the place from where they are originating, hence they will suffer something called a time delay or lag. Now, if the soft photons are getting delayed, then we call it as a soft lag or reverberation lag. And if the hard photons are getting delayed, we call it as a hard lag. Now, this is a timing analysis that we have done for the Markadian 704. Where what we have done here is we have taken two light curves in two different energy band, one in the soft energy band and one in the hard energy band. We did something called a Fourier transform of these two light curves and then multiplied it with the complex conjugate of 1 and then got something called the phase lag and converted the phase lag into time lag, and in that way we got the time lag at different frequency ranges. Here I will tell that these green dots are from the lower flux state observation and the red one is from the higher flux state configuration. Now I will tell the lag prediction how it should be if it is a perfect reflecting model. So reflection model predicts that if you have a high flux state, then the soft lag amplitude should be higher and vice versa. So from this particular source, it is by Khara, 2013, IRAS. This source clearly shows that this green portion is the high flux state and the red portion is for the low flux state. You can see the lag energy lag frequency spectra. Here we see that this green one is having much higher soft lag amplitude compared to the red one. But what we have found is completely different. Uh, we have found that our low flux state is having more amplitude of soft lag. So we have done energy lag spectra, and we have not found any difference with the in the observations, although there was a difference of the flux. We have found this energy lag spectra in the frequency range of 1 into 10 to the power 3 and 3 into 10 to the power 3 hertz. It generally reveals what are the spectral components that are behind this lag. Further, we did the spectral analysis to properly correlate our work with the timing analysis. As most of the aging spectra can be fitted with a reflection model, we have used something called the Elixir LPCP model here. Uh, these are the parameters, the height, gamma, and these are the parameters for the reflection model. And we have found that there is no significant variation in this, although there is a flux variation. So what could be the reason of the flux variation and the observed lags? So we modeled it with the ZXI PCF model. It is an absorption model. It considers a partial covering over the supermassive black hole, and hence from that we have found something interesting, that our low flux state was having much more covering fraction. It's 0.86 as compared to the high flux states. So this is the total model that we have used, Gaussian line for the FEK alpha line at 6.4 keV. So this is our result, that we have found no variation in the lag, although there was a flux variation of 40%. Reflection model predicts that when the reflection is high or the flux is high, we should have a greater soft lag amplitude, but we didn't find that. We found something completely different, and hence we have suggested that there was a presence of cloud when the source was in a low flux state, and because of that cloud the soft lag was getting increased. It was not the reflection that was causing the increase in the lag. We can conclude that it is good to model the whole spectra with a reflection model, but sometimes we need to account for different models, like partial covering model for this particular source, to understand the whole scenario. Now it is very important to understand the real reason of lag, because if it is a purely reflective model supporting AGN, we use this soft lag amplitude to constrain the mass of the supermassive black hole. Now if we are calculating the soft lag wrong, then the mass will be estimated wrong. We can further do studies on different aging using AstroSat, ExpoSat, NewStar. XM Newton is already there. It will help us to understand better the accretion structure and the mass of the supermassive black hole constraining. This is the references that I have used, and my data that I have used can be accessed through the HESARC website. Thank you. Thank you for giving me this opportunity.
Thank you, Develina. We have time for one quick question. AstroSat has not observed it. Maybe ExpoSat will observe it. ExpoSat will observe it. We are planning to write one proposal based on these results. That is the idea. Okay, thank you. Now let us call for next speaker, Komail Murtaza. And the title of the talk is "A Limelight on the Ultimate Source of Energy of the Stars."
Hello, good afternoon. Thank you, everyone. Thank you. It was really nice. I am Komail Murtaza. I newly researched. Still, my courseworks are going. It will be a just review paper. In the sense of astronomy, I would like to say that it is like a pulsar. I heard it's like a moon showing the pulsar, its brightness. After listening all the talks earlier than me, so it will be a moon showing, boasting about his brightness in front of pulsars. So kindly, I thought it will be DC and other guys. So kindly bear with me. Bear with me. So today my talk will be on the ultimate source of energy. I'm a newly born research scholar in the Department of Physics under the supervision of Priya ma'am. Today my content of discussion will be actually I will be talking about star formations. These are my content of discussions. I will have an introduction about star formation, review of the previous literatures, and the proposed model which have studied star formations. And so in the course of we will find the research gaps. So I will be talking about a little just look over the research gaps and finally conclusions. So when we talk about these are the theories, directly we know that star formation is call it stellar formations. Stars are formed through stellar formations, and usually we know stars are formed when through the large giant clouds, which are called it GMCs, giant molecular clouds. So due to shock waves or turbulences in the space, or due to the inner gravitational interactions, these come closer closer, and they are from the dense regions which are called flamings, where there is a maximum probability of star formation. So these are the various theories which have been stated in the process of star formation. First is the triggering events, like due to the pulsar or heavy neutron star or supernova explosions, there will be a triggering shock waves are produced, which may result into the star formation. So there are a few theories which will the supporting. One is the triggering event, another is formation of protostars, and then it is accretion district. Since you have already heard about most of the things, so I come directly to the main. This through pictograph, I would like to represent my model. Since in the beginning, you will see these are almost whole gas cloud, GMCs, giant molecular clouds would be like a whole near about 2,000 astronomical units. This much large space clouds will be spread over, and due to gravitational clouds, they will come closer, and through, or you can say, shock waves, or due to the supernova explosions or shock waves, they come closer. Due to this gravitational collapse, they will be accumulated to a point regions where in the third image you can see like all the mass will be accreted at the center, where due to its higher density, it creates a like space for like nuclear fusion reactions, where the initial nuclear fusion reaction starts and the where we call protostars form it. In the next steps, in order to conserve the total angular momentum, this neutron star, this star ejects some jets in the upward and downward directions. This is just a basic BC in order to conserve total angular momentum. Some jets are released about. So after that accretion, since you have heard too much about the accretion disks in the previous talks, so once this accretion disks form it, the inner core or accreted material is in the center, and rest the whole disk slowly in order to preserve the angular momentum, at some points there is a small accretions where later planet formation is there. So in the last, so you can see where the planets have been formed after the final star being formed. Now the star up to since in the beginning it will form nuclear fusion of hydrogen fusion will be there, and later it will go to up to higher elements up to iron formation. So this, so when we see the stars in the galaxy, we see that there are usually three regions where, like when we talk about galaxy, there are three. Normally we talk about three regions of the galaxy. One is the halo region, another is the disk, and the third is the nuclear bulge. So usually in the halo region, there are older stars are usually created or thrown out in the halo region. While in the disk region, there are newly regions. These are the regions disks where newly stars are formed. and there is the nuclear bulge where there will be maximum star formation and maximum nuclear fusion reactions, or new protostars will be there. So on the same basis, there are like I have shown one graph where on the typical density of like in our galaxy we have like there that image where you are seeing association open cluster and global clusters. The density as you go from association stars, when there is a star formation, few stars combine are they are gravitationally bound systems. Those stars are called global. They form in a globular clusters, where few systems are not gravitationally bound. So they are in the open clusters, and in association stars, these are the not gravitationally bound, and they are free. But they move relative like together in a relation. So these are called association stars. So we see these three types of stars. So these there is one in short in general in this graph you can see some color depicting colors. The green and red regions are where there is new protostar formation regions where you can see maximum star formation. Actually, those you can see some pulses type something of different colors. These pulses are actually the filaments where two clouds merge together, two GMCs, giant molecular clouds merge, and they form a length, like you can say a merger, like regions where there is a maximum probability of star formation. So when most of the regions are black. These are the white regions where there is least star. These are the whites where there is least star. No star formation take place. So for that, I like in order to look for all this, I made a little literature build-ups. So in support of these star formation theories, we have few like supporting models which says how stars are formed and how they are being like governing how these are. So one is gravitational collapse. This star formation may be due to the gravitational collapse. And earlier I said when two masses, we know from the basic we say that when two masses are there from the basic Newton equations, G divided by r square gravitational pull. This due to gravitational pull between two massive things, they come under gravitational force, and one heavier object will be attracted towards the like the simple gravitational only, which will be. So then another theory is turbulence fragmentation model, which states that due to pulsar shock waves or supernova explosion, continuous flow of shock waves makes these giant molecular clouds come together and form the regions of which we have seen earlier only. And one these are the regions that are like star formation model. There are other models also which defines star formation. Two of the models only I specified. One was the gravitational collapse and another was the turbulence fragmentation. So in the proper now research gaps, but since still we know that these are the gravitational collapse and turbulence are the accepted model, and gravitational one is the more effective one. But still there are still gaps where we do not know exactly how the exact precisely how the star formation might have taken place. So in order to have the, like we don't know initially in the initial condition for the star formation, despite being knowing that the gravitational collapse is a vital or it is a pivotal for the star formation. Okay, fragmentation and multiplicity. These are the few gaps. We know the magnetic fields are thought to be they are playing significant role in the star formation, but still there are slight discrepancies in order to properly define the star formation. So this is another thing which we would like to which I would like to study. And another more chemical composition of protostar materials. There is another this also another discrepancy which we would like to study. So then I would like to, due to insufficient time, I would like to conclude. I am like in my conclusion, I would like to come to my conclusion, addressing these research gaps which I have addressed earlier. Whereas like through observation studies using telescope and instrument across the electromagnetic spectrum, theoretical modeling and simulations may be helpful in order to properly understand the star formation and supporting the prevailing theories and maybe building a new theory. So collaborative effort between the astronomers and physicists and the computational scientists would be grateful. And few of my references are there. Thank you very much. Thank you for listening. Any questions?
Thank you. One quick question. Okay, so let us wrap up this session and thank you all the speakers who gave their wonderful talk. They have presented the research work and all the best. Thank you. Let us move on to, hand over the mic to Rizwan. Dr.
So the online speakers just be online. So we'll just start the next session in 5 minutes. There is a tea outside. We'll have quick tea and come back. Okay. So before that, I invite Shehbaz to propose vote of thanks for Dr. Sriram. Okay. So next session we have 5 or 4 presentations. So please have tea and come back even before 5 minutes. So that okay.
Good afternoon, everyone, and the esteemed guest. I am Muhammad Sawaj, research scholar from Department of Physics, Maulana Azad National Urdu University. Thank you for Dr. Sriram. This is the wonderful speech. Thank you.